Hello everybody. Let's go ahead and talk about confidence intervals. We just had a discussion about heterogeneity. We've been through all that stuff on distributions, univariate statistics. So now we really are prepared to talk about confidence intervals and hypothesis testing. It's a big topic, so I'll break it up into two separate sections. Let's start with confidence intervals. So let's just go ahead and provide an example of what a confidence interval would look like. Then we'll go back and we'll provide definitions. I'll even go through and talk about all the different components, but then I'll take another run at it, kind of a logical perspective of confidence intervals, trying to understand them. So let's just start by looking at the equation, looking at how we would calculate the confidence interval of a population proportion. We would calculate that by taking the confidence interval, the population proportion, P, would be equal to an estimate of the population proportion, plus or minus a z-score derived from the Gaussian distribution, and we'll talk about that. Take the square root of the population proportion times 1 minus the population proportion, all divided by n, where n is the number of samples available. Now, what we have to acknowledge right now is that this has to be an approximation, because the fact that we do not have access to the true population proportion. So we indicate with a hat the fact that these are estimates of the population proportion. Now, I've done that right now. Later on, I'm not going to keep doing that, but we have to acknowledge that we don't have the true population proportion. You can see the paradox there. Otherwise, what would be the issue of a confidence interval around it? So this is, now what are the components of this equation? The first component is a z-score. We call it a z-score. Put an alpha there. We'll talk about the fact that it's at a specific alpha level. So the z-score is derived from the Gaussian distribution. This tells us how many standard deviations to capture a specific alpha level. So we specify the alpha level, and then from that we can get the specific z-score we should use. So for instance, if we had an alpha level of 0.05, we could then go to this table right here. Now, the thing is, at an alpha level of 0.05 or 5%, we in fact are dealing with a problem that is symmetric. It is known as a two-tailed test. We could have a proportion that could be higher or lower than the true population proportion. And so we would expect that there is a possibility of values that go negative and values that go positive, or higher and lower. So we got to consider both of the tails when we're talking about confidence interval, lower and upper confidence intervals. Here's the lower one, here's the upper. So at our level of 5%, we have to divide that 5%. And so we want the tail up to 25%. Effectively, we're just calculating the P025, or the 2.5 percentile from the Gaussian distribution. That's all we're doing from this table, and we're just looking it up. Okay. Now on the other end, we'll also have the 2.5, but now this is going to be the 97.5, or the P97.5, or the 97.5 percentile. Okay. So now what we do is we just look up this value from this table, and this table is just a convenient way to look up these specific values, these z-scores for specific levels. And so in our case, we want to look up the 0.025, and if we do that, we find it right here in the table. And so what it tells us is that the z-score will be negative 1.9, but the table provides a little bit more precision. If you look up at the columns, it gives us the second decimal. So we know what we're looking for is negative 1.96. But we're going to be considering not just the lower tail, but also the upper tail. In other words, the lower bound of the confidence interval and the upper bound of the confidence interval. So we'll just say plus or minus 1.96 is the z-score values we should be using to calculate the confidence interval for the proportion given an alpha at 5%. So that's it. That's how we would calculate a confidence interval. Admittedly, not with a lot of explanation right now, but don't worry. You know me, I'm kind of wordy, so there will be lots of different discussions we'll get. So let's start out by defining a confidence interval. We have a very practical definition here, and what we'll say is that a confidence interval is the representation of the uncertainty in a summary statistic as a range. It has a lower and upper bound. It's an interval with a lower and an upper bound based on a specific probability interval known as the confidence level. So how would we communicate a confidence interval? What would it look like? And so let's try it. There is a 95% probability, and often you'll hear this specifically in the media. 19 times out of 20 would be the same as 95% probability, right? That a true reservoir net to gross is between 26 and 36%. And so if that thing we're sampling, reservoir net to gross, if its error has a distribution that's Gaussian, our confidence intervals and the fundamental model we're using looks just like this. The estimate would be right in the middle there, 31%, and we're saying that there's a 95% probability that we have between 26 and 36% for our net to gross. That's our confidence interval. This is very powerful because you imagine if you're communicating to your management, my estimate of net to gross is 31%, and I'm 95% confident that I'm between 26 and 36% net to gross. So that's exactly what we're getting to. I showed the equation on the previous slide, and this is the resulting product, and this is the conceptual, well, the actual model you should have in your mind of what we're doing. So how does this get used in industry? The language of uncertainty is ubiquitous within industry. Decision makers use uncertainty. In fact, if you're working directly with decision analysts and others who are working in that field, you'll find they work directly with those uncertainties. Those involved in geostatistical methodologies produce uncertainty models all the time, and that gets passed through to decision making, and we make optimum decisions in the presence of uncertainty. So providing uncertainty models speaks directly to your upper level management. It's always had a really big impact in my career. I was always able to provide uncertainties. So they need it. That way they can understand the significance of your results and the uncertainty in your results. If you show them two numbers and you don't show them confidence intervals, they're two statistics about confidence intervals. For all they know, they could be the same thing. They could be statistically indistinguishable. You got to show them that they're statistically significantly different from each other. That's much more powerful. A lot of scientists and engineers do not know how to do this. In fact, I experienced this over my 15 or so years in industry, that many forgot their standard statistics courses from their engineering or their geoscience degrees. Or maybe they never really were taught it, but this is very powerful, and having this in your toolkit will help you differentiate yourself. Sorry, that's my soapbox. I can't help myself. Yeah. I think what I teach is important. Well, you have to excuse me. I just had a student come in. I just explained something from the assignment to them, so I'm back again. Let's go ahead and we'll keep going. Let's do a little bit of a review on some of the nomenclature. And so going back to an original discussion on statistics, we defined the sample. We had a population. You recall that we typically work with the sample because we are engaged in subsurface problems. Sometimes you could have the whole population. So we have like a limited sampling from the population. For us, the population might be the entire reservoir. Samples might be just the information we have available at well locations, cores and logs and so forth. Of course, there are examples where we could be dealing with the whole population. That may happen within downstream and refining, where we're measuring, metering what's going on. Or maybe we have a smart field where we're concerned about the way this whole system behaves and reacts. And so we've sampled at regular intervals. We know what's going on. We're tracking it. But typically we're going to just have a sample available to us. And so when we have a sample, we'll denote it as for a proportion. We'll say it's an estimate of the proportion. If we have the entire population proportion, we'll just have it as P. A mean will be an X bar if it's from a sample. If we're talking about the mean of the sample, it's X bar. If we're talking about the population mean, much trickier, right? That's an inference problem in many of our cases. Then we're talking about mu. If we're talking about standard deviation, S would be for the sample, sigma would be for the population, variance, we just square it. And so the uncertainty in a mean or a proportion, the sample mean will be distributed with a Gaussian distribution, n for normal, with a mean equal to the population mean and a standard deviation equal to the population standard deviation divided by the square root of the number of samples. And this is valid if we have enough samples. Sometimes in literature you'll see 15, sometimes you'll see 30. It depends where you go. In general, for this class, we'll make it pretty clear. We'll have small sizes, which will be less than 15 or so, and we'll have big sample sets, which are more on the order of 50 or 100. So we won't make it ambiguous. The proportion, uncertainty in the proportion, is going to be distributed with a normal distribution around the population proportion, with the standard deviation being the square root of the proportion times 1 minus the proportion divided by n. Now we have the same criteria where we'll say that the number of samples inside the proportion, or things that are counted as in, must be greater than or equal to 15. That's how we define small sample size there, or large enough sample size. But we also have to say that things are without or outside must also meet that criteria for us to consider this to be valid. Confidence intervals. Let's talk further about confidence intervals. We've already defined this. We talked about the idea of a confidence interval as being stated such as a 95% confidence that population mean will fall in this interval. If a sampling distribution is normal, then a 95% confidence interval would be equal to the concept of the point estimate plus or minus a score, which would be a z-score if it's Gaussian distributed, times the standard error. Now, if it's Gaussian distributed, 95% confidence interval, as we looked up in that previous table, is equal to 1.96, and that would be our z-score, and we would apply that to the standard error. Those previous equations we showed on the slide back here for the taking the standard deviation and dividing by the square root of n is the standard error for a mean. This is the standard error for a proportion. And so depending on the statistic, we'll have a different way to calculate the standard error component. But the z-score the score will just be dependent on the type of distribution we're working with, such as the z-score. Now, one thing that we got to clear up right away is a 95% confidence interval does not mean that 95% chance that a sample data lie within an interval. We can't say the confidence interval in the mean porosity is equal to between 12% and 16%, and then say I expect the very next well or the very next sample of porosity to be between there. No, that would be a prediction interval. If you're talking about the interval for a next sample, that's a prediction interval. That's the uncertainty in the next sample. A confidence interval relates to the reliability of an estimation procedure, an estimate of the average, an estimate of the variance, and so forth. So just let's not get that mixed up when we're talking about confidence intervals to start thinking that they're prediction intervals. It's always related to something, some type of statistic that we're estimating. So let's go back and remind ourselves of the previous example and the form for calculating the confidence intervals in a population proportion. Once again, the confidence interval will be in the population proportion will be equal to the estimate of the population proportion, I should say, plus or minus the z-score multiplied by the standard error. And so we've already talked about that. We know how to look up from the table for a z-score in order to calculate that, and we've already explained the concept of a two-tailed test. So we take alpha and divide it between both of the tails, and we look up the P025, and we look up the P975 in order to calculate the associated confidence intervals, lower and upper interval bounds. Now, of course, with the Gaussian distribution, it's symmetric, so as soon as you've looked up one of them, it's just a matter of making the other one positive, the first one's negative, and so it's pretty straightforward. What's another way to think about confidence intervals? What does a 95% confidence mean? So if we're talking about proportions or fraction, and we've developed a confidence interval for it, and we're working at the 95% confidence interval, so we have proportion estimate from the sample data plus or minus 1.96 standard error. And so we go ahead and calculate that. What in fact is that? And the way to think about it is that in 95% of cases, the population, the true population, falls within that confidence interval. And so we have our sample statistics. And you could imagine if we had different data sets available to us, just randomly collecting different data, for that number of data, we would have different intervals. In fact, our confidence interval is going to be sensitive to the data that's available to us. But you see what's happening. If we took all of those possibilities of different data we have, and we plot them here, but the true population proportion is that red line, a 95% confidence interval says that 95% of the time, the true is going to be inside of our interval. And so that's really cool. That's a neat way to think about what a confidence interval really is. 95% of the time, the true parameter is going to be in that interval. And so once again, we could show it like this. We could have a situation where we have an estimate of the proportion with limited data. We calculate the 95% confidence interval, and this time we're within the true population proportion is in fact in. And we do it again. Well, 5% of the time at a 95% confidence level are going to be in fact outside. And so here's an example where we have the estimate, we have the confidence interval shown here, and the true is outside. And so we have to accept that. We have to accept that for a 95% confidence level, 5% of the time, the true is actually going to be outside of that. So here's a kind of an interesting thought. Given what we've already talked about standard error, what do you think will happen if you increase n to these confidence intervals? Just give that some thought. And what will happen if we change the level? So in general, what we can say is that if we increase n, remember n was in the denominator of standard error, more samples, we would expect that these confidence intervals will actually shrink. But we would also expect that the estimate of the true parameter will get closer. So it'll all balance out. That's really cool. If you increase the level, what would happen? Well, if we have a 95% level and then we change it to 99% level, this will expand because now 99% of the time, our confidence intervals will now contain the true parameter. Yeah, very interesting, right? Okay, so let's just solidify the concept around confidence levels, alpha levels, and so forth. And so, in general, if you have a, we've been talking 95. So let's go back to 95 confidence level. Well, the alpha level is just going to be the probability of the true parameter being outside that confidence level. So it's 1 minus the confidence level, it's 5%. Your type 1 error probability is in fact the probability of supporting the alternative hypothesis when the null hypothesis is true. Now we'll get into that in the next lecture when we talk about hypothesis testing. What does that mean? It means that you falsely reject. It's a false positive. You're deciding that the situation is not as expected in the null hypothesis when in fact it was still part of the same distribution, and you had a 5% chance of doing that. The z-score is simply going to be the value that we use in order to calculate the upper and lower bound of the confidence interval from the Gaussian distribution. And so this z-score right here is the p 97.5. We've taken the 5% alpha and divided it between upper and lower tail, 2.5% at the top. The negative, we could also do the negative 1.96, which would be the p 0.25 from the Gaussian distribution. So our confidence interval looks like this. So why don't we just use a very small alpha? You could do that. you could say, well, I'm not comfortable with ever having a type 1 error, that I don't want to ever falsely reject the null hypothesis. And so you could set your alpha level as very small. And that's what we have here with a confidence level of 99%. Now we're talking about only rejecting things that happen 1 out of 100 times in a false reject. And so that sounds better. Sounds like a good idea. The problem is you now have a test or a method that becomes very insensitive. You will most often fail to reject the null hypothesis, and we'll talk more about that later. But you could also represent your confidence interval using a 99% confidence level. And what will happen is it'll just become so wide, it becomes hard to interpret. And it'll make, if you have different sample sets being compared to each other, they'll start to overlap, and everything will look very much the same because you're so worried about falsely rejecting a null hypothesis. You want to be too inclusive. You got to discriminate. You need to put a little bit of sensitivity on it. And so 95 is pretty standard. For confidence intervals, sometimes we'll use the t-distribution. We've talked about it when we talked about distribution. It has fatter tails. That's the scientific way to describe it, which just simply means that if you compare it to a Gaussian distribution, which would be this red line right here, a t-distribution with degrees of freedom approaching infinity, that would be very close to basically a Gaussian distribution. If you compare it, when we have very few degrees of freedom, the t-distribution has these fat tails. It loses its peakedness. It becomes more, as far as kurtosis goes, it becomes more platykurtic, and it gets these wider tails and less peak in the middle, right? And so as sample size is large, the t-distribution will actually start to, the degrees of freedom is just equal to number of samples minus 1. So the t-distribution will approach the normal distribution. And so when we parameterize the t-distribution now, we have to specify the alpha, which would be, if we're dealing with a 5% alpha, we would have to divide it by 2 in order to account for the fact that we're working with a two-tailed test, or sometimes there's functions available in Excel where it automatically does the divide for you. We'll show it to you when we do examples. But you've got to specify alpha, and you also have to specify the degrees of freedom. So the cumulative probability and the degrees of freedom, because the shape of the distribution changes where you have more samples available. Confidence intervals, let's just make a couple comments comparing the t-score and the z-score. When do you use a t-distribution, student t-distribution, versus the Gaussian distribution with the z-score? Recall the score is applied to the standard error to get the interval. It's accounting for the shape, and I'll talk more about that pretty quickly here. It's dependent on the shape of the distribution. The z-score only depends on the level. There's no degrees of freedom for a Gaussian distribution. The t-score depends on the level and the degrees of freedom, df, degrees of freedom shorthand. As sample size is large, degrees of freedom is equal to number of samples minus 1. The t-distribution approaches the normal distribution. And so the standard we could set, and I know I said 15 previously in the slides, and I've mentioned that. Use Gaussian. You should know the population standard deviation, and you must have a number of data greater than 2 or less than, greater than or equal to 30. That's a standard that you often read online. In this class, we'll only concern ourselves with having a large enough sample size for our practical use of our statistics. We'll say you have to have enough data, and we'll set that standard as a small data set being something less than 15 or so. In that case, use, it's 30, use t. If it's, greater than like 50 or so, we'll be using the Gaussian, and we'll never have examples of problems where it's kind of spanning the middle, but it's the same type of thing. Now we look up the different the values for the t-distribution, but now we're also accounting for degrees of freedom, which are shown right here, and we also have the confidence level in order to look up the t-score values. So we got to work with both of them now. We will commonly do it in Excel. In an assignment, like a quiz, I may provide you with a table and get you to look it up. So let's just talk a little bit more about this. Let's provide a practical example that will work out together. Confidence interval of a population mean. So the sample mean should be distributed, if we have enough samples, as Gaussian, distributed around the population mean. And the population standard, standard deviation is equal to the standard error, which is the standard deviation of the population divided by the square root of the number of samples. We only have the sample mean and variance to work with, or the sample standard deviation. We don't have the population parameters. And so we're forced to make an approximation and say, well, we're going to base the distribution of the sample around the t-distribution with an alpha divided by 2 because it's a two-tailed test, and we're going to use the sample standard deviation divided by number of samples. Now once again, if the number of samples is large enough, we'll say it's all okay and we can go ahead and use the Gaussian distribution. How would we calculate this? Well, if we have an example where we have, well, just first of all, how we'd calculate it would be we could calculate the t-score by using the Excel command of t-inverse, two-tail. If you use the two-tail variant, you put alpha as the actual alpha level, 0.05 if it's a 5% alpha level. And then n minus 1 for the degrees of freedom, where n is the number of samples. If you just use the t-inverse function, go ahead and put in the 2.5% or 0.025 here, because Excel is not accounting for the two-tail, and you're just asking it to give you the t-score value using the cumulative probability, which would be the first tail, which would be at 2.5%. And same thing as before, you're going to have n minus 1, of course. So we have an example right here. We have a sample set where we have n equals to 100 samples. We have the standard deviation of the samples, the sample standard deviation of 2%, and we have the sample mean at 14%. What's the confidence interval in this case? Well, we can go ahead, it doesn't matter, we can go ahead and use the t-distribution. Even though it's quite a few samples, we should be okay using Gaussian, but we'll go ahead and use the t-distribution, and we'll go ahead and solve this problem. So 95% confidence interval in the sample mean is going to be plus or minus, since it's a two-tailed test, we're going to take alpha divided by 2, t-score of that, and multiply by the standard error, which is the sample standard deviation divided by the square root of n. We substitute that in, and we'll find that we in fact have a result of 14% plus or minus 0.79. It's going to be symmetric. The distribution of the sample statistic is in fact a t-distribution, which is symmetric, just like the Gaussian distribution is symmetric. So that would be our confidence interval. That's all we have to do. It's not too bad. Here's another example. And so in this example, we have permeability values. 400 millidarcies was the sample mean of permeability. The sample standard deviation was 50 millidarcies, and we had only 12 samples. We can go ahead and substitute this into the equation. So what is the confidence interval for the mean? And that will be equal to the sample mean plus or minus the two-tailed t-score multiplied by the standard deviation divided by the square root of number of data. You substitute that in, and you'll find out the 95% probability interval that the true mean permeability 95% probability that true mean permeability is in this interval 400 plus or minus 31.7 millidarcies. So what can that information do for you? Well, if we understand how our statistics are distributed and their uncertainties, we could use this in all different types of hypothesis testing, communication, and so forth, and we'll get into that shortly. It'd probably be a good idea to provide a little bit more information about degrees of freedom. Degrees of freedom. Two different ways to go at it. In sampling, it's a number of independent pieces of information that go into estimating a parameter. For dynamic systems, you could talk about the number of independent ways that the dynamic system can move. We're going to represent it in our equations, and people across the board will use df for degrees of freedom. They'll also use dof, and they'll also use nu, the Greek character nu. Let's take a really quick illustrative example. We're trying to estimate the sum of squares, or an average sum of squares, effectively a variance. We have our set of samples available to us, so we have n samples available to us to inform the statistic, but in order to calculate this statistic, we had to assume knowledge about the mean, but we're forced to work with the sample mean, And that's why we find ourselves saying that the degrees of freedom is equal to 1 minus n pieces of information, number of independent pieces of information, but we had to give up 1, we had to make an assumption, and so we lose 1, that's the minus 1. So I found when I went through this before with my students last term that they struggled a bit, so let me try taking another run at confidence intervals. This will go quicker, and we'll just kind of talk it through a bit. So the problem is you want to estimate the mean porosity of your reservoir. This is important because it impacts oil in place directly. The average porosity is 15%. If you increase it by 5%, you increase volumetrics available for natural resources by 5%. And so we got to get this right. So what's the uncertainty in that estimate? Standard error is the uncertainty in an estimate in standard deviations. So standard error, we know it from theory. It's the sample standard deviation divided by the square root of n. That is the standard error in standard deviations for the uncertainty in the mean. So this is pretty useful. We have from that equation what the uncertainty is. How much spread standard error is going to be in standard deviation, so it's the measure of the amount of spread in that estimate. So if we have an average porosity of 15%, we can calculate standard error. We had 16 samples. Let's assume we had 16 samples and sample standard deviation was 2. So sample standard error in the mean of that porosity, the average porosity, is going to be s over square root of n, 2 over square root of 16. I made it easy math on purpose. That will be equal to 1/2% in porosity units, just porosity. So that's our uncertainty. So you could go back to your boss and you could report the uncertainty in average porosity is 15% plus or minus 1/2%. So 14.5 to 15.5% for the first standard deviation. The average porosity would be 15% plus or minus 1.5% for 3 standard deviations. So that would be between 13.5 and 16.5% porosity. So that's good. You could provide that as an uncertainty model. So you're good to go. But here's the problem. Is it good enough? What's the probability of being between your 3 standard deviations, 13.5 and 16.5% porosity? It doesn't help if you provide an interval, but you don't know the probability of the true mean porosity being in that interval. Your confidence interval is not useful. You need to know the probability. What do you need in order to know the probability? Well, the distribution could be very different. It could be platykurtic for kurtosis. It could be leptokurtic. It could have a neutral or a Gaussian type of kurtosis. And so it could mesokurtic. It could be a whole bunch of different things could be going on with the shape. You need to know the shape. You need to know the entire distribution. That's exactly why we use those Z and T scores, and we rely on theory that tells us about how certain sample statistics are distributed, so we can get the probabilities. So we need to know what will be the distribution shape. So if we were to take our 3 standard deviations, plus and minus, minus and plus right here, and we calculate it using theory that tells us the shape of the distribution would be student T in this case, and we go ahead and look that up, what you'll find is that our interval of plus or minus 3 standard deviations for the distribution shape we would expect is now containing 99.6% of the probability. In other words, our confidence level is 99.6%. That happened just by accident, just by us making an assumption of 3 standard deviations. Confidence interval is way too high. The confidence level is way too high. It would not be helpful to decision making. We need to switch to perhaps a 95% significance level, or I should say a 95% confidence level, an alpha of 5%. And so we need to switch that. And so how are we going to do that? Well, that's not too bad. We know the distribution shape is going to be student T. We can go ahead and look up, since 5% alpha at a 95% confidence level, we look up the P 2.5% and the P 97.5% given the degrees of freedom that we have. And now we get a new value for ourselves, and we find out how many, so this this calculation right here is going to tell us how many standard deviations we need to use. That is our t-score. And our t-score is going to be negative and positive 2.11. And that's what we can apply to the standard error, which was 0.5%. And the result is now we have our t-score times 0.5%. And so now we have 15% porosity, average porosity for our reservoir, plus or minus 1.6% porosity with a 95% confidence. We could also say 19 times out of 20. So you see what's happened here is we needed, theory gave us the amount of spread in the measure of standard error, and that was calculated just knowing sample statistics and the number of data. And then theory provided us the distribution shape, student t, and all we had to do was provide alpha level and degrees of freedom and put them both together, and now we have a precise interval for containing a specific proportion or probability, I should say, probability of containing the true value of the average porosity, the inaccessible true value of average porosity, which is pretty useful. So what do we learn? Standard error tells us about the uncertainty dispersion in the measure, but we still need distribution shape. We know distributions, specific distributions occur for different processes. Averages and proportions tend to be Gaussian, student t of too few samples. Variance or average of squares will tend to be chi-squared. And so we calculate the statistic and score from the standardized distribution. So we'll calculate that score, a t-score, or a z-score for a Gaussian distribution. From the standard distribution, it's providing it to us in standard deviations, and then we multiply it by the standard error. We're rescaling the standard error based on what the shape tells us of how many standard deviations we need to move. We're rescaling. It's pretty useful. So what's happening here? We calculate the score from a standardized distribution, mean or mean of 0, standard deviation of 1. We multiply by the standard error to rescale it for our problem. So we had started with a Z statistic with a lower bound on a 0, 1 Gaussian distribution, Gaussian if we have enough samples. And what we've done is we've shifted it and rescaled it using the standard error, which tells us about exactly how wide it should be, how many standard deviations. And of course, we're adding the estimate of the property, the mean, in. So now our uncertainty distribution is Gaussian, rescaled to be centered at the estimate or the sample mean, with the standard deviation being dictated by specifically the number of samples and the sample statistics and so forth. So that's what we're doing. Does the rescaling work? Can we just go ahead and take the results from a standard 0, 1 distribution and rescale them? It turns out you can. It works perfectly. The more general form of that distribution rescaling is called affine correction. It's to scale values from a set of samples or from a distribution to change the mean and standard deviation, but the shape stays the same. The full form would be the initial value you put in, y initial, subtract out the sample mean, so you center it at 0, scale it by the target standard deviation divided by the original standard deviation, and add the target standard deviation, add the target mean in, and that will shift it back to the right location. In our case, the initial mean and standard deviations are 1 because we're looking up the z-score and t-score values from a standard normal or standard student t distribution. And so this equation simplifies. The initial mean and standard deviations are going to be mean is 0, standard deviation is 1, and so this is going to become 1, this is going to become 0. And so we're able to go ahead and simplify the equation down to this, and this is exactly what we're doing. The confidence interval is going to be based on the standard error multiplied by the t statistic or the z statistic, and we're going to add in the estimate value. So just to kind of think this through about exactly what we're doing with those z-scores and the multiplication is we're rescaling a standard distribution to now fit our problem. So they're very useful. I mentioned this before. If you have confidence intervals, there's so much you can do with them. For instance, What if we have this problem where we have two wells with different V shale, fractionous shale, well 1, well 2, 15% and 17%. If you did not provide confidence intervals, I would not be able to tell if those wells are significantly different from each other. Could they in fact be from the same reservoir, or do we expect that they're distinctly different from each other? Maybe we're dealing with different rock, different parts of the subsurface. So if you wanted to try to test that or understand it, we would have to in fact go ahead and use the concept of confidence intervals to be able to do that. Now, you can do it visually by looking at the confidence intervals like that. A much more robust way to do it is to do a hypothesis test, the difference in the means, and if we know how difference in means should be distributed for a variety of different types of situations, we can go ahead and use that to formulate a test. And so this gets us into hypothesis testing. So we transition from confidence intervals into hypothesis testing right away. Now, let's just finish up with a couple examples of a confidence interval. Geologist has 200 representative samples. There's no bias in the samples. That's important. Of facies in your reservoir unit, what is the confidence interval for facies proportions? I'll give you the equations right here. The estimate proportion from the sample data was 0.7. They had a number of samples of 200. Alpha level was 5%. That means the confidence level is 95%. I'll give you the answer in 3, 2, 1. So how are we going to do it? So we have enough samples that we could go ahead and just use the Z-score. And so assume Gaussian. There wouldn't be any difference with the T or the Z statistic at this point, so it's simpler for us. So we'll go ahead and just use the Z-score. We're going to account for the fact that it's a two-tailed test, so we're going to take Z-score of alpha divided by 2. That's the only parameter we need. Alpha is 5%, so we're going to look up the 2.5%. The standard error of a proportion is going to be of an estimate. A proportion will be the estimate of the proportion, 1 minus the proportion, divided by n number of samples. You substitute everything in, and now we get the proportion of a specific facies will be 70% plus or minus about 6.3%. And so if we go ahead, we could provide a confidence interval of anything between 64 and 76%, 95% of the time the true population proportion of that facies should fall in there. And that we can take directly and report on. That's a valid uncertainty model. So once again, a reminder of the equations we would use. It's shown right here. Let's go ahead and do an example number 2. In this example here, geologist has a representative sample of facies. There's 10 samples available from a reservoir unit. What's the confidence interval in the facies proportion? We have 0.7 proportion of sandstone, 10 samples, where once again alpha is equal to 5%, confidence level is 95%. This is a small sample size. We're going to need to use the t distribution as shown here. I'll show you the answer in 3, 2, 1. So here we use the t distribution. So we're going to be working with the t distribution. With the parameters for alpha will be alpha divided by 2. So we're explicitly accounting for the fact we have a two-tailed test, so we're going to be working with a cumulative probability or alpha level of 2.5%, and our degrees of freedom are n minus 1, 10 samples, 9. We substitute this all in. We're going to find out now that we have the confidence interval in the proportion of that facies is going to be 70% plus or minus 32.8%. And so if we were to go ahead and calculate that interval, we now get anything between 37% and 103%. Now, of course, there's no physical constraint here. There's nothing here that said you can't have more than 100%. We know that's invalid physically. That can't happen. But it's just showing us just how wide these uncertainties are in fact here. Now, if you had assumed a Gaussian distribution instead, for the case here where you have these 10 samples, where we know that really won't be valid, it should be different here, right? These 10 samples is not very many samples. Look what happens. Our confidence interval is much smaller. the t-distribution had much fatter tails given those few number of data available to us. I'll just leave you with one final example. So here's an example where we have, and this is provided in the course notes I can put on GitHub, where we have V shale estimated over various levels within, or depths intervals within a reservoir. That's the red line right here. It's not as useful. There's no uncertainty around it. And so what we could do is level by level, we have different numbers of data available to us. And at the same level, confidence level, or alpha level, I should say, excuse me, we can go ahead and calculate the lower and upper confidence intervals at the 95% confidence level. And if we do that layer by layer, look at that. It's pretty cool. It gets wider because we've got fewer samples at the bottom. We lose some of our wells as we get deeper within the reservoir. But look at how powerful that is. Because now if somebody asks you, is that V shale trend or fraction of shale trend significant? You can look at it and say, yeah, when you get deeper, what actually happens below the datum, some stratigraphic datum at 0, when you get deeper below, the change is significant enough that these are clearly outside of each other's confidence levels from each other. If this slope had been small compared to the width of these confidence intervals, then you could have said, well, you know, that might just be noise. It might not be a real message to really focus too much on. So this is just a nice, useful application. So that's it, the end of our discussion about confidence intervals. We're going to transition right now into hypothesis testing, and I'll do that in a separate video. Thank you for your attention, and let me know if you have any comments or ideas. Okay.